Okay, this is section 3.1, the beginning of chapter 3, and it's got 6 sections to it. We'll get the first today and the second one tomorrow, and then you're just gonna have to kind of, you can hold on to stuff and you come back to it later. Okay? Maybe as we take the section, we'll see. We'll see. Not that many questions you have and stuff like that. Now, before we go on, I need to tell you this, and if you would just take my advice, I'm older and wiser than you. You're gonna have these 2 sections to do, and if you wait until the Sunday night before you come back and try to do them, you will have forgotten what you learned. And other people say, well, if I do them early, I'll forget what I learned. Not quite as easily you won't, because you will expose your mind to this content with a little bit of time involved and fought through the fight a little bit. You will remember it better if you will do it soon, so it doesn't hang over your head the whole dang time. I'm not trying to make busy work. I'm trying to, you will have expended more mental energy to get it, which means it will stay with you, rather than just the mental energy that you will apply while I'm lecturing, and then you let it sit and get lost, leak out your ears for 2 weeks. And then try to do it, you won't be able to. But you will retain it longer if you will do it soon while it's fresh on your mind. I'm just telling you. Okay? If you choose to do it the other way and procrastinate, you may have a little bit more trouble getting caught up when you get back. Okay? All right. I forgot to tell you, the title of this thing, chapter 3, is, I think, quadratics. Yeah, quadratic equations and complex numbers. Complex numbers, we'll hit that tomorrow, as a matter of fact. Because if you're looking on page 90, it has the title of the chapter, and it says we're going to solve quadratic equations today. We're going to do complex numbers in 3.2, completing the square in 3.3, which we are not going to do. We're not doing that section. We'll use the quadratic formula in 3.4. We'll solve nonlinear systems in 3.5. That'll be fun. And quadratic inequalities, which are pretty easy. It's a pretty easy small step to go from equations to inequalities when it happens. So we'll do that. So today's lesson is going to be on solving quadratic equations, which you've already had some experience doing. So this shouldn't be, most of it shouldn't be new. Some of it might be, a little bit. Most of it should be stuff that you're going to dredge up from your memories that you've already got, and it won't be that hard for you to learn the second time. All right, so if you get your eyes on page 94, which is where things begin, just a really, really quick explanation to anybody who's watching this video. It's homecoming. The reason I'm dressed so weird is because it's mismatch day.
I like it.
All right. Okay, here we go. We are going to learn 3 ways of solving quadratics depending on the situation. One of them is going to be by graphing, so I have your graphing calculators handy. One of them is going to be using square roots, which only happens in certain instances. And the other one is going to be by factoring, which only happens in certain instances. So we'll learn those 3 things. Get my calculator out. It's not. You have to take it. Bring it back. I'm not going to check it out. Get it back after you've used it. All righty, here we go. The very first one, example 1, the instructions are solve each equation by graphing. And what we're looking for, folks, if you'll look very carefully at the equation we're going to solve, which is x squared minus x minus 6 equals 0. You're used to seeing it from the previous chapter. You're used to seeing something very like this, looking like this. Y equals x squared minus x minus 6. And then we would ask, in the previous chapter, we would ask you to graph that. You'd start out by doing negative b over 2a and finding the vertex by plugging it in. And then you would observe that a is positive, so it'll open up. And it's only 1, so you go out 1, up 1, out 1, up 3, out 1, up 5. Yeah? That's not what we're doing. We are letting the y value with what we studied last. This has billions of points on it. This has at most 2. Because we're letting the y value be 0. And if y is 0, I'm going to put this over here so it can be seen on the video. If the y value is 0, it means it hasn't gone anywhere It means we're looking for points that are not up or down, that we're looking for points that are on the x-axis, because that's where y is 0. So we're cutting it down from if we're trying to figure out where the millions of points fit together to where we're finding at most 2. And I say at most 2 because some parabolas, as you've seen, open up like this. If they open up, they can open down and they hit it twice too as well. Sometimes they open up like this, and sometimes they open up like this. And in those cases, when we're solving by graphing, what we're looking for is when this parabola has a y value of 0. In other words, in this case, we're looking for that value of x and that value of x. In this one, we're looking for this value of x, and in this one, there won't be any. So this, if you get a graph like this, there will be 2 solutions. If you get a graph like this, there will be 1 solution. And if you get a graph like this, there won't be any at all. And it doesn't matter if it opens downward. Hang on just a second. If it opens downward, we could still possibly get 2, right?
Yep.
We might still possibly get 1. Now, I am hitting the negative x-axis, but it could just easily as hit it over here. Or it might open like this, in which case there won't be any. So it doesn't matter whether it opens up or down. What matters is how many times it hits the x-axis. That handle your question?
No, I was just wondering, how are you supposed to graph it if you only have 1 point?
You won't even have 1 point. We're going to graph it and see where it hits the x-axis. That's our goal.
Okay.
I'm going to teach you how to handle that, okay? I'm just saying 3 different situations might possibly occur in each problem. Okay, so now what I want to do, I'm going to get rid of this. Now what we want to do is actually consider this one that's equal to 0, not equal to y, but equal to 0. And we want to graph this left side of it in y1. So we're going to put this in y1 of our calculator. So go to graph. Make sure that your plots are all off and that your y values are empty. So in y1, with all the plots off, you know what I mean by plots off, right?
Yep.
Nothing's blackened.
Yep.
Okay. Go to y1 and type in. Do you know how to type in x squared? Do you know where the square button is?
Yep.
Right here. Okay. X squared minus x minus 6. And I would always start, unless the problem has context. This doesn't. This is just a quadratic, no context. You know what I mean by context?
Yes.
It's not a story problem. It's just a problem that we're looking at to try to study.
Yeah.
And if it's out of context, I mean, there's no context to it at all, then I would go to Zoom Standard to get yourself a window. That's Zoom 6. And this graph does happen to hit twice. Now, I can't remember from one class to the next. Have I taught you how to find the zeros on the graph? With a left bound and a right bound?
Yeah.
I have?
Yes.
Okay, now let's everybody go find the left one. You go second, and the trace key, which is calc, 0. We get to the left of it with either with your cursor, or you can type something in if you want. Get to the right of it, and I find that the leftmost one is -2. Anybody's following? Looks like that. And if you do the zeroing, the second calc and zeroing, then it lands at x equals -2. Now notice that the y equals 0, but that's what we wanted. This is the thing that we knew. So we're looking for is zeros. They call them zeros because that's where the value of the function is 0. There's no y value to it, it's just 0. And so we end up with x equals 2. What's the other one? Oh, -2 and 3, right? If you find the other 0. So that's called solving by graphing. Now, you've got a second one in example 2. It's a little bit different because it's not ready to be graphed yet. Sometimes you have to do a little bit of algebra work on it. It's not very hard algebra work. We have -2x squared. This is what it says. -2x squared minus 2 equals 4x. This was not ready to be graphed. Why? We've got to set it equal to 0 first. Which means that 4x is either got to come over here to the left, or both of those terms on the left need to go over there to the right. I'm going to do it both ways because I want to show you what's happening. And it doesn't matter which way, but I want to show you both ways. If I bring the 4x over here, I'm going to tuck it in where I've been taught that it belongs, which is right there, and then bring the -2 home there. Is that okay? You don't have to do it that way. Your calculator doesn't care. But have a good habit. That's a good thing to do. So go back to your y equals screen and hit clear. And now that it's been set equal to 0 properly, when we brought the 4x over, change sign, we need to graph that one. So type in negative first. -2x squared minus 4x -2. Now you're all aware that this negative right here comes from the bottom row of your calculator and these two come from the right side. They're different. They're understood differently. Okay, so hit that graph. Ooh, that appears to hit only once. It looks like it hits at -1, doesn't it?
Yeah.
So here's what you can do. If you don't want to go through the zeroing process, you can just go second calc a value rather than a 0 at -1, because that's what you suspect it is. And sure enough, the y value there is 0. So you get something like that. Get the y value equals 0. So this has only one. X equals -1, sorry. X equals -1, and that's a single solution. What would have happened, so that you don't get spooked by this too much, what would have happened if instead, this thing right here, I decided to go this way with it? Check it out and see. Check it out and see what would have happened. As a matter of fact, put this one in Y2 so you can compare it to what we had here. Put it in Y2. Okay, so we get something like this if we did it that other way. However, both graphs have this for a solution. So does it matter which one that you graphed? I mean, one is very different from the other. But when what we're looking for is the 0 of it, it doesn't really matter which one. They both have the same 0. And I don't know why you would, but if in this first one you wanted to kick all of those over there and make it -x² + x + 6, you would have had a parabola that opened downward, but it would have hit the x-axis in the same place. And that's what we're after. So it doesn't matter which one. Okay, they're much different parabolas, so that's not the case. They are different from each other. That's the same 0. Everybody understand how to graph or how to solve by graphing? Okay, example 2. Before I do example 2, I need to give you a brief introduction to the behavior of, the looks of some quadratics. I should have graphed those on there. I keep forgetting that thing's there. This is your standard form quadratic that you're trying to solve. If I say 0 instead of y, and I put ax² + bx + c, a, b, and c are just numbers, right? Now, my question is, will you still have a quadratic equation if the value of c is 0? What qualifies something as being quadratic?
X².
An x² term, right? So if c is 0, we'll still have an x² term. Will we still have a quadratic if b is 0? Okay, that just means this is called, by the way, this is the quadratic term. This is the linear term because it's like mx + b, you know what I mean? This is the linear term. This is the constant. So you're telling me the constant could be 0 and we'd still have a quadratic. The linear term's coefficient could be 0 and we still have a quadratic?
Yeah.
Can the quadratic term's coefficient be 0? No, because if so, you lose it and you're back to linear. So what I'm saying is that you can have a quadratic if either one of these is 0, but this one has to be something other than 0. And here's what I'm telling you. The next thing that we're going to study together is when this one is 0. B. If b is 0, then you have a quadratic. Oops. You have a quadratic of this form. Okay. Now, hang in here with me. I've got about 2 more minutes of talking about this particular type and why it's unique. I'll come back to this in just a minute. Consider this one with me for just a minute here. If I have 0 equals, let's say 3x² + 2x - 1. If I asked you to solve that using algebra, pencil and paper, if you were an Algebra 1 student that didn't know anything about this, you might start by doing something like this. You might start by saying, okay, I got to solve that. That means I got to get x by itself. So I'm going to bring that 3x² over here and 2x - 1. Then I'm going to divide it by -3. And then when I get to there, I'm going to square root. And that'll be the solution for x. That's false because you have x equals something with an x in it still. You go, okay. So it wasn't the x² I was supposed to solve for. I'm going to try and solve for this x right here. So you say, okay, that's going to be, if I bring that over, that'd be negative 2x equals 3x squared minus 1. And then I'll divide everything by negative 2, and I have 3x squared minus 1 over negative 2. That's the solution. No, it isn't, because you still have x in terms of x. What I'm saying is you cannot isolate this x or this x without having the other one on the other side, which means you cannot solve this equation in a usual, conventional way by trying to isolate the x. Do you understand that? However, if I have one like this, where I have 0 equals 2x squared plus 7. No, better make it minus. I gotta dodge the other bullet. Anyway, if you have something like this, which is like this one, a is 2 and c is negative 7, then you can solve this conventional. This term is missing. That was part of the problem. So if I bring the 7 over, I have 7 equals 2x squared. If I divide by 2, and then if I square root, I get this. And by the way, this is a big by the way, shh, it's always plus or minus. But you can isolate x and have it equal to something that doesn't have an x in it if that middle term, that linear term, is missing, because x occurs in only one term instead of 2. In this case, this process is called extracting square roots, because right here you extracted the 2 roots by square rooting to get x by itself. Do you all understand why this has to be plus or minus?
Mm-hmm.
You do?
Mm-hmm.
If you do, then don't forget it. Don't leave this off when you're solving. If ever you have to square root in the process of solving for x, then whatever's on the other side of x after square rooting has to have a plus or minus on it, because there's 2 possibilities that you could square to get 7/2. Either the square root of 7/2 or the negative square root of 7/2. You can square either one and get 7/2 back. You got to have them both. By the way, in this instance right here, these 2 numbers, I don't know what this number is. It's just an irrational number. But whatever this number is, are the values. Somebody find that for me. Square root of 7/2. So I got something to work with.
1.87.
Oh, wait.
1.87.
Well, yeah, about almost 1.9, right? So what this is saying is that in this parabola right here that I just made up, 2x squared minus 7, if you were to graph that parabola, it would cross about right here and about right here. Those are the zeros of the parabola. And in its initial offering here, this was positive and it's kind of vertically stretched, so it's going to be kind of skinny and it's going to come up like this. I have no idea where where it hits, but it's going to, well, actually I do. Yeah, it's going to hit down 7. It's going to be clear down here. If you remember your transformations, we do know where that's going to hit. But it hits the x-axis here and here and starts at negative 7. That would be a graph of this quadratic. Vertically stretched by 2, down 7. Got it? Yeah? Okay. That doesn't feel right. I wonder if it's, I think it is 7. Okay. So this process is called extracting square roots and can only be applied if the linear term is missing, meaning b is 0. It's the only time you can apply it. So take a look in your books at example 2 on page 95. And please notice with me, there are 3 problems to do there. And look, the A one has only an x squared, no x terms, yeah? So you would bring the 31 over to join the 49, divided by 4 and square root. Is that going too fast?
Divide the whole.
You'd have to first add 31 to the other side.
Yes. Okay.
Then divide that result by 4.
Okay.
And then square root the result.
Okay.
Are we clear on that or not really?
Yeah.
Look at the next one. Same situation, right? Except for this one presents a huge problem. 3x squared plus 9 equals 0. That is of this form I was talking about, with the b part missing, so extracting square roots is a possibility. So we have 3x squared plus 9 equals 0. It's of this form right here, and so the first thing I would do is kick the 9 over and divide by 3, and then square root. No solution. Because you cannot, there is nothing in this question, that what's asking the question, what we're asking right there is, what number can I square that will give me a negative? And the answer is there aren't any. You cannot square any number and take any number by itself, multiply by itself and get a negative. So if you're ever called on to square root a negative, there is no solution. This is one of those parabolas that, look at this one. This is the regular parabola, vertically stretched by 3, but moved up 9. This one's way the heck up here and opening up. See how it's never going to hit the x? No solution, because you're called upon to square root a negative. You can't do that. We good?
Yep.
Okay. And then look at the last one. This one's a little odd. The C part. You might not think it is of this form, but it is. It's just strange looking. So I have 2/5 x plus 3 squared equals 5. 2/5 and then x plus 3 squared equals 5. And what I'm saying is that it's not x that's squared. It's a binomial that's squared, but still it's of this form. A would be the 2/5. X squared would really be x plus 3 squared, and the C is on the other side. They've already taken it over. Do you see it is of the form? Okay. So what we do now is we try to isolate the squared part, just like we tried to isolate the squared part here. Do the same thing here, the squared part, by first multiplying by 5/2 on both sides. You following?
Okay.
We're going to multiply by the reciprocal to get rid of that.
Okay.
Everybody clear?
Yes.
Okay, good. That leaves me with x plus 3 squared equals, this is an understood 100, so it's 25/2. You okay? Then we're going to square root, just like we did right here, even though we didn't get anything viable, but we're going to square root it to get that x by itself, but at this time it'll be x plus 3 that we get by itself, which will be plus or minus the square root of 5 or 25/2, which is 5/√2. Am I going too fast? Square root of 25 is 5. Square root of 2 can't be done, so we leave it. Then we bring the 3 over. That will finish solving for x, but there's a slight problem with this. We bring the 3 over and we tuck it in front of that. It looks like this. And in the process, we're going to have to rationalize this denominator, which is really 5√2/2. That's how it should be written. Because it is improper. Let me put it up here so everybody can see. This right here, when I have the plus or minus 5 over the square root of 2. Does everybody understand how we got to there? I mean, right to here. Yeah? It is improper to leave the square root of 2 in the denominator of a fraction. You're not done with it. It's just as improper as leaving a fraction like this. That's improper to do. You need to do more to it, which is simplify it. With radicals, you can't leave a radical in the denominator. And so we do this really cool thing. We multiply by 1. That won't change the value of it, right? But the 1 is going to look like this. √2/√2. Anything over itself is 1. So I'm really multiplying by 1. But I'm doing it in such a way that this √2 times this √2, which is √4, is actually 2. No more radical. But the numerator is going to be 5√2. So what I'm saying is that this and this are equivalent. This one's proper because there's no radical in the denominator. So that's what I did from there to there, is I rationalized the denominator in my head by doing this in my head. And if you need to actually write it out for a while, you can. But that's the proper answer. This is improper to leave that radical in the denominator. Okay? And there is a reason why. And it's the most old and archaic and horrible reason out there. And if you want, I can explain to you why you have to rationalize the denominator. And it's completely obsolete. But we still have to do it because you will have professors who really should be retired that are still working. And they'll want you to do this. It's ridiculous. But you still have to do it. ACT test writers and ISAT test writers still think this is important. I am old and I think it's stupid. So there you go. Okay. I can show you someday why it is that it used to be important to do that. It is no longer important, but we still have to do it. Crazy why we can't evolve. Okay. All right. So if you hit something like that and you have to square root and it's gross and ugly, make sure you don't leave radicals in the denominator, and then isolate the 3 by, and when you bring this over, tuck it in front so that the plus or minus is between two things rather than leading. It's just proper. It's just more fun. It looks nicer. It's better. Okay. So that's your little lesson on extracting square roots. And extracting square roots only applies if this term is missing. Or in other words, if b is 0. Otherwise, it doesn't. You can't use it. Moving on. Okay. Now we're going to solve by factoring. This is something that you're familiar with. You may have forgotten some of the details since you've been in Algebra 1, but we'll bring them back to your memories. Before I do it, I want to ask you a couple questions so you can see where we're headed. If I have a number, any number, times any other number, and the product is 0, what do you know for sure?
One of the numbers is 0.
Yep, one of them's got to be 0, maybe both. Right? Is that true?
Yes.
So if I write A like this and B like this, one of them's got to be 0. If it's this one that is the 0, then X has to be 4, since 4 minus 4 is 0. If it's this one that's 0, then X has to be -2, since -2 plus 2 is 0. Which one is it? The answer is they both get their shot at it. So the answer is that. Gotta get them both. And these are the two places that this quadratic, if you foiled it out, that these two guys, this quadratic equation will graph in such a way that it hits the x-axis here and here. That's what you found. So what we've got to do is take standard form quadratics and turn them into this so that we can do this to them. And that's called factoring. And a lot of people like it. Most people don't. Okay. So take a look at example 3. It says x squared minus 4x equals 45. X squared minus 4x equals 45. Okay. And that's in improper form. I need to bring that 45 over, right? To set the thing equal to 0, I'll put everything in the right order. Do you all know how to factor that? Let me play a little game with you before I factor that. We used to do this. I used to do this with my kids. Well, they aren't my kids, but might as well be. When they were growing up, traveling in the car, instead of watching videos, we would do this. They hate me for it, but they're very good at it. Can anybody think of, and when you think of it, raise your hand, don't blurt it out. Can anyone think of two numbers that multiply to be 24 that add up to 11? More hands here. Multiply to be 24, but add up to 11. What do you think? Back there in the back, way back at this row.
Oh, 8 times 3.
8 and 3? Are those the two numbers that satisfy that?
Yes.
Okay. Can you think of two numbers that multiply to be 15 that subtract to be 2? That's easy, right? Because there's only two numbers that multiply to be 15. How about this one? By the way, it was 2 and 5 and 2, right? 5 and 3. I mean, 5 and 3 that subtract to be 2. Okay. Try this one. Factors of 36 that add up to 20. Factors of 36 that add up to 20. Tommy?
18 too.
There you go. Did y'all get that right? I mean, those of you had your hands up. How about factors of 30 that subtract to be 7?
Oh, God, it's 7.
Yeah.
First off, 10 and 3.
Yeah.
Do you understand the game? This is how you use it for factoring. You read, and math is weird because math is not restricted like regular reading where we read from left to right. When you use this little game that we just played, you look, first of all, this has to be a 1 or it doesn't work. But most of the time it is. Not every time. But if this is a 1 right here, then this is how you play the game. You find factors of 45. Two things that multiply to be 45 that subtract to be 4. We're ignoring this sign until later. So this is what we're talking about. Factors of this that do this to make this. This is important. Factors of 45 that subtract to be 4. Can you think of any? 5 and 9. Then that's what you put in the back end of these factors, 5 and 9. What goes in the front end is splitting this x squared up. And I always teach my kids to consider the signs last. Now, if you want these two guys to subtract to be -4, then the 9's got to be negative. So that when you combine them together, you have a -9 and a 5 that gives you -4. That's how you assign the signs. Does that make any sense? So that equals 0, which means that x is either -5 or 9, yeah?
Yes.
This quadratic right here will hit the x-axis at -5 and 9. Okay? That's how you play the game.
Like
So-
at one point, or are those both points?
No, this is not a point. This is the x value. It will cross. The parabola will cross here and here. And it will open upward because the x squared is positive.
So, Ms. J, I got a question.
Yeah.
Does that only work with whole numbers, or will you get decimals and fractions?
For factoring,
Yeah,
it doesn't work for that.
it doesn't work.
But
for
you won't have anything but whole numbers to deal with.
that. Okay.
Okay.
Today or just the whole lesson?
Ever.
In this class.
Oh, perfect.
Yay.
So ever is.
Where they require you to factor it anyway. They may put things in there, but they'll let you solve it with this.
Okay.
Okay, so let's try another one. Let's do another one that's kind of like this before we leave it. Let's do x squared minus 7x minus 30 equals 0. So we write down, first of all, observe that that's a 1. Otherwise, this game won't work. Shh. That's a 1. So we're going to write this down like this. We're going to split it up and put an x in the front of both. Then we play our little game and we put the signs down here last. So don't worry about the signs. Don't worry about that sign. We ask ourselves what?
Factor 30, that subtract to 7.
And that's, we just did this one a minute ago. Marcel said it was 10 and 3, right? Does it matter which one's where? No, it doesn't.
Which one's?
What matters now is
One's positive.
what's
Negative.
positive?
-10.
A -10 and a positive 3, so we get the -7 out of it. You see? Equals 0. Now, what would happen if I had changed it like this? What would happen in our factoring?
The 3 would have to be negative and positive.
This would be negative, and this would be positive, so that when we combine them, we get a positive. Now, let's pretend it was this at the beginning, and we got this. That means that x is either -10 or 3. Again, that's where it crosses as it opens upward. Y'all see it? This is, by the way, you guys, this is like the P and the Q in the intercept form.
Magic.
All right. So now what happens if this number in front is not 1? Then the game gets a little harder.
Never mind.
Oh, I know what to do.
Shh. We're going to do that with this next one. And it's going to be 2x squared minus 11x plus 12. 2x squared minus 11x plus 12 equals 0. Now, 2 happens to be a prime number. There is only one way to split it up, and that's 2 and 1. So when we write down our sets of parentheses, we write down 2x in one of them and x in the other. And it doesn't matter which. I just always lead off with the big one there. It doesn't matter. And the things that go here and here still have to be factors of 12. But now we got a 2 screwing things up. So this is what I do if I'm wondering how to do this, or I'm somebody like you just starting out. I write down the factors of 12. 1 times 12, 2 times 6, 3 times 4. Those are the only possibilities, right? Okay. So pick one.
1 and 12.
All right. If I put a 1 here and a 12 here, here's how you check it. This sign is still very important. You take this number, this product. Forget the x's, just these two numbers. You take this outside one, which is 24, and add 1. You get 25, right? It's not 11. So it's not these two. At least not in that order.
Different.
So we put a 12 here and a 1 here, and I get 2 plus 12, and that's 14. Closer, but not 11. So it isn't this. We've tried it in both orders. Do you understand what I'm saying? No?
Not really.
Yes.
Okay, so let me put the 12 here and the 1 here again. To check to see if I've got the right combination, I'm trying to get 11 by taking this product, which is 2,
Oh.
and add this one, which is 12. 2 and 12 is 14. I need it to be 11,
Ah.
and it's not. So, and I tried it with the 12 over here and the 1 over here, and it was even worse. So I've decided 1 and 12 aren't it, because I tried it in both different reckons, and I did not get an 11.
It's the 3 and the 4.
You want to do 3, 4 next?
Yep.
All right.
But the
Put a,
3,
shh. Put a 3 and a 4 here. Here's how you test it. You take this product, which is
8, and you do this. This is a very important sign. You add 3. 8 and 3 is? Then that's the right combination. However, 11 is negative, so I'm going to need a negative 8 and a negative 3 to get this to happen. See it? Okay, still equal to 0, which means that if I continue solving, letting each one of these have their shot at being 0, x is either 4, that's the easy one. What's this one? It's 3 halves. Let me show you how you can get it quickly. Shh. What we're really asking is this. When is 2x minus 3 equal to 0? Aren't we asking that? That's what we're wondering. So we kick the 3 over, we get 2x equals 3, and we divide, we get 3 halves. Now you can run that 3 to mine or on paper anytime you want, but observe. When you set this equal to 0, the result will always be this number over this number, opposite sign. The opposite sign happens as soon as you kick that 3 over. It'll always be back over front, opposite sign. So back over front, opposite of that is positive. So those are your 2 answers. So if there's a number in front here and you can't tell exactly what it is, like it was easy here, it was just 4. But this one, you're wondering what that is, take the back over the front, opposite sign. You'll hear me say that all the time. It's just like doing this every time. It's just that you don't need to because it's always the same pattern. Back over front, opposite sign. Okay, so that's how that solution comes about. And the factoring is much more difficult. You got to consider each of these. And if it doesn't work one way, you got to try it the other before you abandon that combination like we did 1 and 12. We tried 3 and 4 because he said we should. I tried it in the order 3, 4, and it worked. Quite often, you'll hit the correct combination before you get too far through the list. And if you're really good at it, especially with a number like 2, if you've done it enough times, you can tell what these are going to be. But you got to really think about it. And if you can't think about it, and all that processing is too tough, then write down your possibilities and write them here and write them here. And if it doesn't work, abandon it. Try the next one here and here until you get a hit, which is this product plus this product gives you that number. And then decide on your signs. It's one way to factor. And I like it best because it's much, much more close to what happens when you FOIL. It's just reversing a FOIL. Same ideas. Okay. Hang in there. We've got 2 more problems to do. And the first one seems really daunting. It's a tough problem.
Number 4.
Example 5 on page 97. You need to get your eyes there and you need to get your mind focused on what I'm about to tell you. Here's the situation. A monthly teen magazine has 48,000 subscribers. So it only stays that way when it charges $20 per annual subscription. If the company starts messing around with the price, then they start messing around with the number of subscribers. Because every time you raise the price on something, there will be a few people unwilling to pay. It's called supply and demand. So this is what they have discovered by doing this. They observed that for each dollar increase in the price, every time they raise it a buck, they lose about 2,000 subscribers. 2,000 people decide, I'm not paying that extra dollar. And if they raise it $2, they'll lose 4,000 subscribers. And if they raise it $3, 6,000. You understand what I'm saying?
Yes.
However, if you lose a few subscribers, but charge all the ones who remain a higher price, perhaps you'll still make more money. So the question is, just exactly what should we do under these circumstances to make the most money? So you got to understand a little bit about revenue, cost, and profit, mostly revenue here. Do you know what revenue is?
Yeah, it's
Anybody
what you
coming?
make. It's the
That's what
money.
everybody else says. It's always what you make, but that can be interpreted a couple of different ways. It's what you bring in.
Yeah. Bring it.
If you sell one item and that's all you sell in your store, the revenue is what's in your cash drawer at the end of the day. That's what you brought in. From that, you can take that big pile of cash and you got to pay your taxes, got to pay your light bill, got to pay your rent, got to pay your insurance, got to pay your employees, a whole bunch of other things. And after you pay all those people, if you've got any money left, that little tiny bit of money you got left is your profit. So revenue, which is the amount you bring in, minus cost, which is what you got to pay out to stay in business, equals profit. But that part of this that we're discussing that I want to talk to you about is how do we determine revenue? For example,
if you're selling, all you sell in your store, that's all you sell is great big large chocolate candy bars, and you sell them for $2 a piece. How much money will you have in your till at the end of the day? If you sold 100 candy bars, $200. What if you sold 50? $100. What if you sold 1,000? 2,000. What if you sold X? 2X. So what I'm saying is what you've just discovered here is that if you take the price that you're asking times the number that you sold, you get your revenue. Does that make sense? So if I write this down as revenue as a function of the number of items sold, that X is the number of items, this is revenue, the amount of money you bring in, it's going to be the number that you sold, and I'm going to write it out like this, the number sold times the price that you're asking. Does that make any sense?
Yep.
The reason why this problem is so hard is because both the number that we're selling and the price that we're asking are moving around. Keep raising the price, we keep losing number sold. Right? So watch how we write this carefully. The very first thing you need to understand is, I'll go ahead and I'll put this to good use right now. You got to understand this 100% wholeheartedly in your brain without question. What X is. X is not the number sold. X is the number of $1 increases. Now, if we're going to raise it in increments of $5 each, then this would still be the number of times that we raise it $5. That's what X is. You got to solve it in your mind. It's the number of dollar increases in this case. So watch how we do it. Watch this. The number sold then is going to be the 48,000 we started with minus 2,000 X. However many times we raise it $1, we're going to lose 2,000 customers. So if I raise it 3 times, I'm going to lose 6,000 customers. Does this make sense or not?
Yeah, it's
Okay.
okay. Yeah.
The price that we are asking right now is $20. And we are going to add to that $1 this many times. And I know in algebra we don't write it that way, but I want to emphasize that it's a dollar increase this many times. If we raise it 3 times, then the price will be $23. You with me? So this is how the number sold and the price are moving around. Now, think with me for just a minute about what would happen if you multiplied this binomial times this one. Do you see that in the very last thing that you would do, you would have a negative x squared term?
Yeah.
See it? Which means this parabola, if we graph this, would look like this. Yeah? So if we want to, by the way, just to put this on a grid so you understand what you're seeing here. This graph represents the number of increases. That's what X is. This right here represents your revenue. This is the Y. X is the number of increases. Do you understand what X and Y represent? So if I found this, that would be my maximum revenue for this many increases. Is that making any sense? Yeah? Okay. So now we will make the calculator do the grunt work, but you still have a little bit of thinking to do. So don't grab your calculators yet. Think with me just a little bit more. Because in this scenario right here, we've got to come up with a window that we'll be able to see this in. So remember what X is. It's the number of dollar increases. Remember, this is a magazine that's charging $20 right now. What do you suppose if we graph this? What do you suppose the X min ought to be? 0. How about an X max? 100, 25, 1,000, 4. Remember what X is?
The number of $1 increases.
The number of $1 increases. How much do you suppose this company is going to raise their price before they decide I'm not going to raise it anymore?
5.
I'm gonna say 10 times. I don't think they'll go much past 30. People don't want to pay $30 for a subscription. I don't care who you are. So I'm gonna say that this is 10. Now, let's talk about the Y min. Remember what Y is? Y is your revenue. What's the revenue right now? 48,000 times 20. Right now, it's 48,000 times 20, isn't it?
Yeah.
We're hoping it goes up by making an adjustment, but we need to get that size of a number, 48,000 times 20. That's nearly $1 million. $960,000 we're making right now. I want to go a little bit before that, just in case our price increases causes the price of our revenue to go down, but not much lower. So I'm going to say that the Y min is 900,000. And right now our revenue is 960,000. So what do you think I ought to let my Y max be, just in case our revenue goes up? Pardon? 2 million? That's a little aggressive.
1 million.
1 million might not be. We're almost there already. I'm going to let it be about 1.2 million. That's just from experience. And if this doesn't work out, or you choose a bad max or whatever, your calculator will show you. These aren't nearly as important as this is very important, the lower one, and these are really important. If you let this go clear out to, or if you let it go from -10 to 10, you'll waste half your screen. Think about the sizes of these things in context. It's called domain and range, people. So everybody go set their window to this. After thinking about it, you set your window, because see, if you just went on a standard screen and graphed this, you wouldn't see anything. Way too tiny. So go to your window and go from 0 to 10. We'll see what that does for us by ones. And then go from 900,000 to 120,000. Okay. By probably, I don't know, 100,000s is your scale. Okay, now now that you set up your window, go to your Y equals screen and dump anything that was in there before. And when you type it, you don't have to do anything to this. You don't have to foil it out or nothing. Just type it just like this with parentheses and everything. So in Y1, type in a parenthesis and then the 48,000 minus 2,000 X. Close it, open another. Plus X. And if you hit graph, you should be able to see something. Not very revealing, but we can see something. We can see the piece of the parabola we need. We can see its maximal. In that window that we chose, that would be what it looks like. And it's not really a great graph, but we can see the maximum. Do you remember how to go find a maximum?
Yes.
So go second calc, a maximum, and go find it. Okay, would anyone like to interpret what they believe this means?
At the maximum amount, you're gonna have like 968,000.
$968,000 is what you expect to pull in?
Yes.
For what price? $22. Because the X value is 2 virtually, right? It's 2, which remember what it means. It means we're going to raise the price $1 twice, and it's already at 20. So the correct interpretation of this, if you understand what's going on, is raise your price to $22 and you will realize a maximum revenue of $968,000. Right?
Yes.
Now, let's think about the reality of this. I don't know what's involved in raising the price and then resubmitting all your subscriptions and have people pay the next year around this extra $2. I don't know if it's going to cost, I don't think it's going to cost or be really hard to do or whatever in a company this size. But you're changing the price to $22 for an additional $8,000 out of $960,000. Nearly $1 million, you're going to realize an increase of $8,000. That may not be worth it. You know what I mean? So all I'm saying is, yes, you will realize a greater revenue, but in the context and the size of these problems, the size of these numbers, it's not gonna be a great increase, but it will increase some. Okay, are you with me? By the way, the people who come up with the data, that is, that they lose about 2,000 customers every dollar that they raise it, the people that come up with this and do the studies to come up with those numbers are called actuaries. And if you like math and you like our capitalist society, you like those a lot, being an actuary is an extremely lucrative, meaning pays a lot, career, and it's fun. I've heard it's really fun. I would think that if I had been a teacher, which I find to be the most fun, that's probably where I would go, is an actuary. Nobody even knows what an actuary is or has heard of it. Boy, is it, if you can get into a bachelor's program, and the only thing's a bachelor's degree, you can make 6 figures right out of college, working for a company. You probably work on a team of actuaries with 3 or 4 or 5 people in it. And you would do all of these studies and make recommendations to the CEOs of large companies about what they should do. Good job. It's fun. Okay, just so you know. One more thing, and this has to do with physics. So now we're going to the sciences rather than the economics. Okay, listen up. This is one of the reasons why studying quadratics is absolutely essential if you're going to go on to college. One of the reasons. If you have the height of an object as a function of time, we're talking about projectile motion again. That's launching things. Cannonballs, footballs, bullets, missiles. These all are called projectiles. And we can predict their vertical height, mind you. If you throw something like this, I'm talking about just the stuff going up and coming down this way, not going out. That's not what we're studying. This is only vertical height of the object. Shh, shh. On Earth, if you measure things in feet, the leading term is negative 16t squared. The next term is v naught, meaning the beginning velocity as it comes out of the end of the barrel. T plus s naught, and that's pronounced s naught, not snot. Okay? And these are pronounced knots. It just means the beginning amount. That's why it's a 0. Sub-zero, we call it S naught, V naught. Initial velocity, initial position. So if you're going to launch a bullet from a hill where the lake down below is your 0 amount, this might be 150 feet up. If I'm going to launch it from the top of this ladder, probably 6 feet. If I'm going to launch it from a well, down in the well, and I'm going to launch something up and out where the ground level is 0, this might be negative 30 feet. Can you see position could be negative? If you launch something upward, initial velocity, initial vertical velocity, not out that way, but the vertical part of it is positive. If you are on a bridge, a great big tall bridge, and you're going to throw a stone off of that bridge instead of just dropping it, you want to huck it like that, then the speed of your arm and that rock as you let it go is negative because you're throwing it down. So this could be positive or negative. This could be positive or negative. Most often they are positive, but they don't have to be. This is always negative 16 if you're doing this stuff on Earth and you're measuring things in feet. It's negative 4.9 if you're measuring things in meters. And it's a totally different number if you're launching things on the moon or Mars or Jupiter or any other planet that you can think of. Because every planet's got its own gravity component. And on Earth, it's negative 16 feet per second per second. Well, it's negative 32 feet per second, but this term is half of the acceleration due to gravity. So, with that in mind, listen. For a science competition, students must design a container that prevents an egg from breaking when dropped from a height of 50 feet. You ever done that? Very, very cool experiment. So they're going to drop it from a height of 50 feet. Here's what we're to do. We're to write a function that gives the height in feet of the container after t seconds, and then to answer this question: how long does the container take to hit the ground? And then we're going to interpret something else when we're done with that. Let's get that done first. So, assuming these kids are science students on Earth, we know that the height of the object is guaranteed to start out negative 16t squared. What's the initial velocity? When they take this box or this container that they've built and they let it go, how fast will it be moving at that instant? It won't be moving at all because they are dropping it, not throwing it. They're just dropping it. And what will the initial position be? 50. So what we have to work with is negative 16t squared plus 50. Notice the b term is missing. Quite often it is when you drop things. Just something to note. So this is how we can predict the height at any time t. If I want to know how long it takes it to hit the ground, what will the height be then? 0. That's why we do things equal to 0 a lot of these times. Now, if we wanted to solve this algebraically with the b term missing, I'd kick the 50 over, divide by negative 16, and square root the result, which would be 25/8. And I don't need the negative because that makes no sense in the context of the problem. We're talking about the amount of time since we dropped it. Negative time isn't going to help us. Oh, sorry. Square root of that. Ha. Square root of that is t. You agree or not?
So already square rooted it. I know.
Because I have to square root this to get t, I have to square root this. And this is a negative negative, so it's positive. I reduced the fraction by taking a 2 out of both and got this, so it's the square root of 25/8.
Okay, yeah.
Okay, so on your home screen, not your graphing screen, on your home screen, take the square root of 25/8. I get 1.77. What you got? Now, graph it. Go to y equals, clear standard, I don't know about standard screen. We might have to design the window. Go to your y equals screen and type this in, because this is what we want to find the zeros of. Negative 16 x, we're going to use x, not t, squared plus 50, and graph that, but we might need to think about the window. Notice this is an initial value of 50, so we want to let the y's be at least 50. I'm going to let my maximum y be 100. No, 80. And I'm going to let the minimum y be 0. Maybe negative 10, so I can see the x-axis. And I'm going to let my x's, I just discovered my x's aren't very big at all. It takes less than 2 seconds. And that's what time is. That's what the x's are. So I'm going to let it go from maybe negative 1 to 3. So I can see everything. Then if I hit graph, I get this parabola. You get a parabola like that? I need you to understand that this piece of the parabola is the only part that makes sense, is from here down, because this is negative time. So only from the peak down is the dropping of this object. So go find the 0. Go calculate a value. I'm sorry, a 0. Left bound, right bound. Hang on. And I find this, voila, 1.77, which is what we got by solving it algebraically. So it takes a little less, not quite, closer to 2 seconds than 1, but less than 2 seconds for it to hit the ground. Now, one last thing and then we'll be done. Hang in there, we're almost out of time anyway. The B part of this says, find and interpret h of 1 minus h of 1.5. First of all, how do you find h of 1? What does that mean to do?
T for 1.
Yeah, right over here in the function, right here, this function that we've got right here, it means replace the t with 1. So what is h of 1? What's the value of it? If you plug 1 in right there, what do you get? Punch some buttons, people. What happens if you let t be 1? The h of 1 means let t be 1. 34. What does that mean in the context of the problem?
1 second. Gone 34.
1 second, exactly 1 second after they dropped it, it is 34 feet up still. What's h of 1.5? Put that in here and do some math. And those of you that aren't doing this, I sure hope you figure it out. Screwing around, doing things I ask you not to, and whatever. Anyway, it's your problem. 14? What does this mean? If I write 14 right here, what does just this number mean? It means after 1.5 seconds, still 14 feet up before hitting. What does this difference mean?
Those 2 times.
By the way, what is the difference? My mistake. 20. What does that 20 mean?
Between those 2 times, it's gone.
between 1 second and 1.5 seconds. In that half-second interval, it's strictly between the 1 second and the 1.5. It's not just any half second, but in the half second between 1 and 1.5, it dropped 20 feet. That's what you write, and you may have to write some words today. How awful for you. Between 1 and 1.5 seconds, the box dropped 20 feet. That's how you interpret that difference in the context of the problem. You okay? Each of these individuals are the heights after this much time. It started out at 50 feet. After exactly 1 second, it's feet up. After 1.5 seconds, it's still 14 feet up, which means between 1 second and 1.5 seconds, it went 20 feet vertically. That's what it means. You good? Okay. You might want to write this down maybe at the top of your assignment so that you can remember it, because you may be called on to remember it without giving you any information. I want to write that down and remember, this is the gravity component, this is the linear velocity component, this is the position component. You may need all of those to do problems like this. In this case, we only needed the first and the last because the object was dropped. Okay? All right, that's it. Here's the assignment.
This is 3.1, correct?
3.1. You ready to write?
Yep.
Here it comes.
Okay, I'm ready.
3 through 23 odd. 24. 25 to 47 odd.
To 47?
47 odd. Then this list: 51, 54, 55, 57, 59, 64, 67, and 68. If you want extra credit on the next test, a few points anyway, then you can do number 75 on a separate sheet of paper. It's extra credit, you don't have to do it, number 75. But if you do it, you have to show me all your work so I'm convinced you know what you're doing. Okay?
Alright.
Alrighty, there's that one.
Pencil
We
drop.
gotta go over the test now.